Okay, it's a great pleasure today to have Professor Daniel Lotz with us today. Daniel is a team leader at Riken Center for Quantum Computing and a professor at the University of Basel in Switzerland. He has won many prizes, fellowships, distinguished memberships, among them Fellow of American Physical Society, Institute of Physics, and then many more. Daniel was actually, I think, a postdoc at IBM a long time ago, where with David DiVincenzo, they actually laid out the very first kind of criteria for what the qubit should actually look like. Now we are decades after that, and we are very, very excited to hear what are the progress in the spin qubits in semiconductors and what is the path for future. So thank you, Daniel, for coming, and I'd love to hear.
Okay, switch here then. Okay, thank you very much for this nice introduction and for inviting me here. So actually, I'm attending next week this workshop, and then the result will be a good opportunity. I was not sure what I should actually talk about here, but it's Colloquium, and it will be from a theory side very soft. So it will be lots of pictures, and I'm open to be stopped at any point, so you can also ask questions. So I have about an hour. I'm not sure I will be able to finish. That's also part of the construct here. That's a bit open-ended. Now, the title, I think, says it, and I should acknowledge a number of collaborators on the list of stuff I will tell. I mean, if I would list all collaborators, there would be many. It's still, I mean, they've been working with me for a very long time. Books. It's down, I don't know what's before it did actually. Yeah, it says something here. It's annoying. So. No, nothing works. Oh, okay, I have to do it. Yeah, sorry. Okay, good. So here's an outline of my talk, what I plan to tell you. So I would like to give a little bit of an overview where the field is and a few topics I'm going to talk about. If you want to read up, I think it's recorded, so you can see this kind of reviews. There are a number of very recent reviews, very nice one in Review of Modern Physics, a very lengthy one just came out by Jason Petter. Workout and more recent one just holds in the systems and many more. Let me say now a few things first to put qubits a little bit into spin qubits a little bit into perspective. So there are a few front runners for quantum computing. My favorite one is here on the top. These are spin qubits. More about it, but of course there are others which are further ahead in the race. If you just count qubits, these are superconducting devices, and other systems are ions, neutral atoms, photons, and so forth. And there's also topological quantum computing, which plays an important role up now in the field. Also, much in terms of qubits has been achieved there. So one can characterize this type of qubits a little bit provocative. I would say spin qubits are small and fast. Small meaning on the scale of a transistor in your chip, and that means we can actually imagine to get on a chip of a square inch or so 100 million qubits, which one would need to operate 10,000 logical qubits. That's a full-fledged quantum computer, just this number. So fault-tolerant quantum computing, FTQC, that's kind of the target. And other systems like superconductors, they're rather big. So in size, they're about a factor of 1,000 bigger. So we are talking about 100 micrometer in length scale versus 100 nanometer. And they're also typically slower and very similar, actually also for ions, atoms, photons, but they have hundreds of qubits. IonQ, for example, has now 30, 40 qubits. IBM, I think I have here companies working on that. IBM has now 400 or so qubits. They are working not really fully as qubits, but I can count them as future qubits. And at least here also the companies investing in this. And topological quantum computing, this is still in the making. Microsoft in particular invests a lot of money there, and there is a very ongoing, interesting discussion in the community whether actually Majoranas have been observed. The basis for a qubit would need 4 Majoranas to define 1 qubit. And it's very clear the Majorana has been found. I think a few of us think actually not, despite the big propaganda Microsoft is making. So, and the big difference also between the field topological computing and the rest is that in topological computing there are many theorists working. Here in the other fields, also many experimentalists and experimental programs are underway. Yeah, here's a slide which I found recently in a article by McKinsey. So here you can see a little bit the investment. So what is big in terms of money. The biggest one is superconducting qubit, so this in terms of millions, 3,500 billions. The estimate has been invested already in this field. Second one is trapped ions. I think most of it goes to IonQ. I think they have now even 3 billion raised on the stock market. And photonic networks and spin qubits. You see the size here. It's not small in comparison in terms of investment, but it's growing. Okay, well, there's also a remark that the platforms for superconducting devices, topological qubits and also spin qubits is actually very similar. And this also explains why many people working in this field can switch from one to the other. And if there's a problem, let's say with Majoranas, that we would switch to Gatemons or spin, Andreev spin qubits. It's a little bit of a family tools. So let me give you now, go more into spin qubits, a little bit of an overview. This is a slide which I got from a colleague here in Quentin, and it demonstrates the development of the field and the variety of the field. It also explains a little bit why spin qubits are not at the level, let's say, like superconducting qubits. In superconducting qubits community, there's basically one design that people have agreed on, the community has agreed on, and most companies, they're working on one particular design. For spin qubits, people still are not sure which one. And this is basically all one material family in terms of silicon or silicon germanium. And there are many, many variations. I have not even listed all of them here. And they can be divided roughly in through 3 directions. So maybe I should say, as you mentioned, this was many years ago. I think it's approaching 25 or even more years. It's getting a little bit embarrassing to say that. I should actually say, from here to here, there's a very important part which I leave out. Maybe I have it here. Oh, because I see Leo sitting in the audience. There should actually be germanium quantum dots in there. They have been very important in the first 10 years or so of the field development. But then gallium arsenide, and gallium arsenide has the problem that it has nuclear spins. And the nuclear spins, they are not very good for the coherence of the spin, and therefore community has switched then to silicon or germanium. And there are kind of 3 different types of qubits one can distinguish. So these are all quantum dot structures here in detail. And I'm very glad now that I don't have to explain this more, because we had just an hour with the students and you learned about the quantum dots. So I think they understand what I'm talking about here. In the differences here, so these are electron spins in some disguises. For example, there's a quantum dot, there's an electron spin trapped here. This you can call a qubit, or 2 electrons, and the gates here confine it and allow them to control these qubits, and the control of the single spin is done by ESR type of setups. where magnetic fields are generated to manipulate the spin. And generating magnetic field is very difficult. AC fields is very small amplitude, and therefore it means it's slow. So even if they have very long coherence times, some of them have actually the record time. I think it's in this one here from Michel Simmons from Sydney. I mean, they have coherence times which go up in seconds. They're very impressive, but it's also difficult to control them fast. And the second type of development is electron spins, where one controls the spin, single spin, by a micromagnet. The magnet which creates a field gradient as indicated here. And this field gradient allows them to have different splittings so that one can address them individually. This is also not really scalable, but the best devices currently are actually based on this, and also in Delft based on this type of technology. There's a third development now which gains more and more momentum, and this is based on valence bands on holes. And holes, especially in germanium, but also in silicon, has a great advantage, and this will be talk here, that there's strong spin orbit. And the spin orbit couples the spin with orbital degrees of freedom, and then you can control orbit by electric fields. Therefore, spin by electric fields. That allows to have a very fast control. So there are many more than what I show here, but this gives you kind of an impression. So the figure of merits one collects here are the T1, T2 times. This is the coherence and relaxation time of the spin, and you can see here coherence time versus years, publication date of many different systems. 3.5, germanium, silicon, silicon 28. That means all nuclear spins are removed. Here, phosphorus, there's an atom impurity in silicon, carbon nanotube, and the times here they go up and up over the years, and there are different times depending on the symbol, but the most important one is T2 start time, and that is kind of increasing. Here is the state of the art by Lieven van der Zijpen's group in Delft with 6 qubits, 6 electron spins under full control in a linear array here, and single qubit properties all characterized. Very nice. 2 qubit fidelities, they're also okay. Fidelities here, that means how precisely you can switch a gate. And ideally, you would like to have 2 to 3 nines, 99.9, then you are kind of in a range where you could say you could scale up that system. They also looked at 3 qubit GHz states. That is kind of reasonable fidelities. But this is just to show that these systems are under high control, and that's kind of what people can do for electrons. But basically, when I give this talk, I have to update it now every month. There's so much stuff coming out. I mean, here is, for example, a release of Intel's chip this summer. They call it the tunnel folds chip with 12 spin qubits in silicon. And this is all you can learn about that chip. They don't tell you more. There's no paper on it. There's just this web page where they say, here's the chip. And a few groups in the world will get access to it. I know a few groups that have now. But unfortunately, there's not much more known. I know that T1, T2 times are very good in these chips. The yield is about 95%. But they can reproduce essentially their device in the same way industry standard. We will see, how far this goes. I think tomorrow, Charlie Tahan will be here, give a talk. He has actually access to this, and he's one of the people from my institute.
Do those work at millikelvin or?
So, yeah. I mean, typically, I will come to temperature. This depends now on the size of the quantum dot. The smaller the quantum dot, the higher the temperature you can have. The levels are larger. So typically, this is 50, 100 millikelvin. So most of the experiments are done in that range. Can also be lower, but now there's also higher temperature. We'll show some data here at the temperature of, I think, up to 7-8 Kelvin. It's already possible. Because of the ice to consume, but this one is smaller temperature. Now, this is from Tarucha's group in Regen, near Tokyo, and in silicon spins. This is kind of a record for the fidelity. It's very high here. not yet 3 nines, but very close to it. And these are the switching times, rapid times, up to a few megahertz, 2 qubit gates, also a few megahertz. So it's actually not so bad. Well, they can also do small algorithms in there, but I think that's just for demonstration purposes. It's not really much done so far. And question to the temperature. So temperature really goes up now, and some of the devices now this measurement at 4 Kelvin, data which go up to 9 Kelvin. I think I might have some slides here. This is possible because the devices become smaller and smaller. What I have shown so far are mostly electrons and the kind of natural candidates for spin qubits. But in these tables, you can see there are also holes now, and I will focus in now a little bit more on holes in these systems, especially in germanium and silicon, and we'll see kind of advantage holes have. So it's it's another story. Quite some time ago, also nearly 20 years or so, we came up, let's look at holes. And at that time, this was rather surprising because holes had a very bad reputation in terms of coherence times. It would be much, much smaller than for electrons. It was known in some optical systems. But we showed that when you confine your system laterally very strongly, then the coherence time, the relaxation times of holes also go up. They can go up as high, even larger than, at least in theory, electrons, first thing, and the second thing is holes have very strong spin orbit. So this is a very typical coupling between momentum and spin. Cubic, for example, here, Dresselhaus spin orbit interaction, and there are different types of Dresselhaus spin orbit interaction, and this can lead to very fast Rabi oscillation. And that is a very useful thing because just by electric gates you can control then your spin. It can go up actually to gigahertz. These were kind of predictions which we made many years ago, and literally it took 15 years, nothing happened. And then people started to work on the systems, especially in germanium, and there's now a lot of progress there. So here is a collection, for example, of germanium. It's called now the quantum information route. So germanium is coming back, so to speak, as a platform of quantum effects. They have become very, very clean. Was Cappucci from Delft, also very nice systems. And what is interesting here is the valence band, so conduction band here, and the valence band is heavy holes and light holes. They behave depending on the geometry. When you start to confine them, quantum confine them in different geometries, whether this is now wire or some hot wire or some two-deck two-dimensional hole gas, they have quite different properties. And this type of geometric dependence we will use now a lot, or is used a lot now in this field. So here just to show the purity of the system, this is from Studenikin's group in Canada, and by now, for the two-dimensional hole gas, they have a mean free pass of about 30 microns. It's quite impressive. Here's one from Scappucci with a new growth setup here, where actually the substrate is no longer silicon. It used to be silicon, here it's now germanium, and then the mean free pass is also very long, more than 20 micrometer, and the quantum mobility reaches a new record. And I think this is now state of the art, almost. Probably there, this just appeared 2 months. Probably I will hear some new data from Delft, but it is very fast progress. And this is the kind of main theme in this field to improve the material. There is a plethora now of different geometries and setups. I will show a few of them. This is just to show there's a lot of work which has happened in recent years, also not in theory, but a lot in experiment. So for example, I should mention this CMOS silicon hole structure from Grenoble, Ivana De Franceschi, with the first really to implement holes and show basically they used a silicon wafer off the shell and rewired the transistor basically to get qubits. This was a breakthrough type of experiment because from then on, engineers in the field, they started to believe that the qubits can be something they can also work with. It's not has to completely reinvent the wheel. Here's a FinFET structure. IBM Basel collaboration. This is probably the best whole structure in the world by Lena Feldhorst, also from Delft, 4 qubits. I will show a few data from there. It's very high fidelities. Yeah, so here FinFETs, these are typical transistors which we have in silicon. They're also in your iPhone, for example, in there. And they can also be used as qubits. So this is a collaboration in Switzerland with University and IBM. And here's a device where kind of coupling has been demonstrated in these systems. So for example, here, this is at the temperature and FinFETs at 3 Kelvin, where T2 has been measured up to 6 microseconds, and the noise can be identified as hyperfine noise, the remaining nuclear spins in the system. The source of noise, which limits the coherence time, is now coming in these systems from charge fluctuations. Because if you have spin orbit, then also charge can couple to the spin via spin orbit. You cannot only control, but it's also a problem. And this charge noise needs to be coherent. And here is, for example, I just showed this this recent work. This is a work which took more than 4 years to calculate. Just to tell you, how complex actually the structure is. I think I might have a slide. I cannot really go into details here, but there are many terms in the Hamiltonian which show coupling between spin and orbital degrees of freedom, and there is no small parameter in there. We had to look at all possible terms in the system, identify them, warping and so forth, calculate and see which one has the strongest contribution or has a contribution to charge noise. And what we found then was, so charge noise basically means you have a split level, a Zeeman level, and this level fluctuates because of charge fluctuations which enter the system via effective spin orbit. But what we found then is that the directional dependence of that charge fluctuations which leads to dephasing, so this is the T2 start time versus electric field. So here's the structure. So let's say a two-dimensional whole gas down here, the electric field which goes perpendicular to the whole gas. Here's the quantum dot confined. We have a magnetic field, let's say in plane. And now the field here, when we change this field on the small value here, then we see that the coherence time can actually be controlled. That's one thing. And the other thing is the direction of the magnetic field. So the angle phi here, the magnetic field takes with respect to this quantum dot, can then lead to sweet spots such that the coherence time can increase by orders of magnitude. And this identification, this realization that there are sweet spots in the system has now motivated many experimental searches for that. And the first one, which has confirmed that, is an experiment also in Grenoble, where they indeed found in their silicon device, whole device, that the direction of the electric field leads to an enhancement of a factor of about 6 of the T2 time. And so we see now that understanding the material, and then also what is very important, the growth direction of the material turns out to be extremely important. So when people now grow this material, we try to tell them, do not do the standard growth. The growth direction 110 is actually much better than the standard. It's one of the messages that we find from here.
Here's the question. So what is actually the origin of the charge noise? Because you would think that at low temperature, very close to 0 Kelvin, all the noise, everything freezes out. Also the two-level fluctuators.
Yeah,
everything freezes out.
Actually, it's not completely known. I showed some picture here from this here. So from Scapucci, he thinks actually that this location are sources of noise. So the charges trapped, they go through the entire system. That the kind of charge fluctuations originate from those. It's something which people measure in terms of noise in this system, and this system here is much less noisy than this system. What exactly and where the charges sit and fluctuate, I think no one really knows. But we can take this as an input. Then we know, what the charge noise is, and through this calculation we can connect then the charge noise which is measured, the to the coherence time of the spin. Yeah, but it's a good question. I mean, let's say in the device from Intel, they know that they have, for example, dangling bonds at the surface. So there's a 2-deck down here, tangling bonds, and these tangling bonds, they can create, for example, artificial or spurious quantum dots or charge fluctuations. And this is why, for example, there are now schemes where they apply some screening gates to screen this kind of fluctuations. So there are many mitigation strategies to use this. But I think this is now highly promising, and this should be much less charge noisy. There are no quantum dots yet in these systems. So yeah, this is also a recent experiment from IBM in whole gases, and they have achieved here, this is why I show it now, the record time in T2 star, which is now 10 microseconds, and this is for holes, and let's say 5 years ago, this was a factor of 100 smaller. This just shows, you know, the kind of the development which goes on. This is very fast, and 3 nines in some of the gates. Fidelity 99.94. So this is, you know, fully scalable in the sense of having these fidelities. From Feldhorst group, very recently, same device now improved. It did very nice measurements, and one of the qubits actually had even 4 nines. It's totally amazing. 20 years ago, no one would have believed that this is ever possible. This is a solid state environment. It's very, very complex, right? I mean, it's really amazing. And what they do is, this is called random benchmarking. So basically, you apply all these gates in a random order to your qubit, and reverse then the motion and see how far away you have gone through the application of these gates. And that gives you then a decay depending on the number of gates you apply here, and from this you can read off then the fidelity. And they did one thing more in this experiment. It also shows now, it goes a step further, namely also to look at the crosstalk. So these are electrostatic environments, and if you manipulate now this dot, then this dot will be influenced by that. And this is also shown, for example, here in these crosstalks from 4 qubits. Then the fidelity goes down, and it's only 2 nines. But this is something where you could say, you know, if this would be scaled up, it would be in the range where we really do qubits. It's not like 400 qubits, which you call qubits. These are really very good qubits. But the effort is more to improve now the quality of the qubits. So let me now say a few words about the theory of holes. I think it's also quite interesting from a theory point of view. So when you go to beyond the Schrödinger equation, in the Dirac equation, there is a term which couples the spin to the orbital angular momentum. And if you are in a solid environment, then it's the orbital angular momentum on the log function, so you have bands, and typically the valence band, it's L equals 1. The spin is 1/2, and that means that the total spin you can get is a 3/2 or 1/2. And if you have a 3/2 total spin, then you have 4 states, plus 3/2, plus 1/2, and the same for minus 1/2. And these are the important spins. These are called the heavy holes and the light hole spins. Oops. The energy spectrum looks like this, band structure, so that's very typical, let's say here for germanium. Here we have heavy light holes, and there's a reduction band, and this is the split off band. This will be total spin 1/2, and this here is total spin 3/2. It's the 4 states. This is described by a very aged Hamiltonian, Luttinger-Kohn Hamiltonian, and this Luttinger-Kohn Hamiltonian is actually really a fantastic cartoon, at least if you stay to this low energy sector. Very often you have to take actually many more bands into account to get an accurate description. And just to give you now a little bit of a flavor how such a spin qubit looks like, it's no longer just a simple spin 1/2. How does a state look like? So the simplest example one can look at is a quantum wire spherical symmetry. Let's say in germanium, there we know that we can approximate the potential cone Hamiltonian spherical approximation, which basically gives me a quadratic term here and a term where the momentum couples to the total spin here as a Kähler product and a square. This is spin free half here. In addition, we have radial confinement, let's say hard wall confinement, and then we can calculate some conserved quantities, total angular momentum along the wire ends up with the angular momentum of the spin, and this we have then as a quantum number to describe the system. So when you write down then the state, so the ground state is then a linear superposition of a free half is a -1/2. So this is a heavy hole, light hole. A heavy hole is a light hole, and here also a heavy hole is a light hole, the opposite spin. But it, the reason why I show this here is it's a superposition of different spin states, and that means at first sight you would think that cannot be very long-lived. It's here, but it's a ground state property. It's a very solid object, and in the end, it has a total spin, effective spin, given here by this quantum number, which is -1/2 and +1/2, and that is sufficient to have it as a spin. And all the material parameters that can be calculated and also measured independently, so we know basically everything about that system. So here's the energy spectrum, low energy spectrum along the wire. Kz, the quantum number along the wire, dispersion relation. So we have a lowest band here, and here at around Kz0, there's a near degeneracy, which would not be very good if we had to live with that. So each line here is twofold degenerate. And for this now, what happens when we apply strain, for example, if we have a wire with a germanium core and a silicon shell around it, then we get the mismatch of lattices. So silicon has a smaller lattice content, and this leads then to a strained system where the silicon has to relax the strain as you go outside. This exerts forces, and this changes the dispersion relation. Is described by the so-called Beer-Pickus Hamiltonian, and when you go in that, then you see that when you add, you have no shell, just germanium alone, nearly degenerate, but when you add a small shell of 1 nanometer only, you get the lifting of degeneracy. This is what is very, very useful, and the games played in this system is strain. And now, what about the spin orbit? So we have now this 4x4 system in the ground state and excited state, so it's 4x4. These are diagonal terms. And now I add an electric field perpendicular, let's say, to the wire. This is this term here, and there's now an additional coupling, which is coming here off diagonal, and this is coming from the Cohn-Lattinger Hamiltonian from this particular term, K dot J. When you project it into the states, these off diagonal terms, it becomes linear in momentum. And it's this term, together with the electric field, which creates a mixing of heavy hole and light hole. So here we have the heavy holes and inside the light holes, and they get mixed now by these off diagonal terms. This is what makes this is a new source of spin orbit interaction. We call this direct Rashba spin orbit interaction, and it's this mixing which one can turn on and off very efficiently. Well, just for experts, standard Rashba is also present, but is much smaller, and this new first order effect leads to a very strong effective spin orbit. For example, there's an experiment now on this type, exactly on this, the wire which I described. So here is a such a wire, germanium core, silicon core shell, another wire grown by Erik Backers and measured in Basel by Zumbühl and colleagues. And there are quantum dots here, and these are the gates. And then so describe this as a double dot bias. And from the energy spectrum as a function of detuning, so you just apply bit voltage and detune the double well potential. Then from level crossing and anti-crossing, we can read off the spin orbit effect from the spin orbit splitting and deduce then the essential parameter, the spin orbit length, and find length scales which are about 50 nanometers for the spin orbit length. And that means I have to move my hole by 50 nanometers to flip the spin. So this is rather short. If you compare this, let's say, with gallium arsenide, you had to do this about 5 micrometer. So it's a factor of 10, 100, actually 100,000 stronger. This is why this material is so interesting. And another effect from this is that you can drive now the spin qubit extremely fast. So here is the Rabi frequency, which you can turn on by a gate voltage. So this is off situation, and you turn it on by just a small change of a gate voltage M here. This is this gate, and it turns on. And you reach then Rabi oscillations, or the driven Rabi oscillations, which are on the order of 500 megahertz. But this was a record for a few weeks, and then it was beaten by a record from China, 600 megahertz, and now the Chinese group has the record of more than a gigahertz. And it all goes back to this spin-orbit coupling, to this relativistic effect, which allows electric control of the spin. And the nice thing is it follows basically the theory.
Do they have it from germanium?
Germanium, yeah, these head wires.
They grow it themselves?
Yeah. So it's in Beijing.
Another question. So can you have both? Can you have fast switching, fast Rabi, and being sensitive to charge noise?
Yeah, it's a very good point. Of course, when you switch on, then you also become very sensitive to the charge noise. And this is why I emphasize here the switch. So in the idle state, you should not, it should be switched off, such that the spin orbit is very, very small, so that the charge fluctuations then, have less effect. So it's only during the switching that charge noise would matter. And so you try then to beat, the system. So when you have very fast switching, then charge noise cannot accumulate, so you can turn it off again. So sweet spots. So these are kind of sweet spots. I will show you. Maybe I have a picture of better sweet spots where you can actually have a sweet spot at a finite gate voltage. So you really can go to 0 and then stay there. Then go in both directions, positive, negative, and turn it on and off. Here, this is another example. So this is an example now for silicon, FinFETs. So these are just a silicon block, and you trench a valley in there, both sides, and then you get a fin. And it's these fins which are used as transistors in our devices. And these can also be used now essentially as wires, nanowires, silicon. And here they have very, very strong directional dependence of where you apply the magnetic field and in which direction you apply the electric field relative to each other. And here, for example, the electric field, which is not very large, you get for this gray line basically divergence in leading order of the spin orbit. And this is basically the point where you operate and where it can go off. Sweet spots, they are also not only for charge noise, but also for the hyperfine interaction. The hyperfine interaction is also very interesting for holes, and they can also control it by electric fields. And it's possible to have in some geometry sweet spots which coincide for charge and for the hyperfine interaction.
Hyperfine comes in dipole.
So hyperfine interaction comes from the nuclear spin, and there are germanium atoms which have nuclear spins. There's only nuclear spin free.
So the contact.
No, right. Sorry, yes. So it's P wave, so there's no contact. Yeah. So you have dipolar hyperfine interaction. But there's also part of it is orbital angular momentum. So there are 3 sources of hyperfine. There's S wave contact, and then the dipolar, and then the orbital. Okay, good. So in the last few minutes, I also want to say something about kind of scalabilities. People have different ideas here. One of them is, for example, to use quantum links. So you have some small units of qubits, hundreds or so, and then basically control them with wires, and then you have some space to connect them by links. And these links could be, for example, given by photons. Let me say a few things now to spin photon coupling. This also has become a very important topic in spin qubits. And the standard way in a cavity, so these are basically cavities, the same strip-like cavities people use for superconducting qubits. And you can couple the spin also to a cavity mode, either through magnetic field, which would be extremely weak, or again through electric field, and then the spin-orbit interaction, which gives you an effective coupling. And the typical coupling considered is a so-called transverse coupling. So you have a field which splits in z direction, your effective spin, and then you couple the photon mode of the cavity in perpendicular direction. This gives then some means to control the spin. You can spin flip the spin, read out the spin, and so forth. You can also get approximate 2 qubit gates. You can couple when you have 2 qubits, 1 and 2 via a photon in a cavity. This can be far apart. The disadvantage with this type of coupling is that it's kind of dispersive and has a limited range of strength. So I just flashed this here. There are quite a few experiments now which have demonstrated coupling of spin to cavities. Here, this is going from charge qubits to spin qubits. I think here is now the most recent one from Grenoble, where they coupled a whole spin qubit to a cavity and reached actually the strong spin photon coupling range here is around 200 megahertz or so. So it's just to say that it's possible. Now, there's also, and this is the nice thing now about Hall again, that one also can have a so-called longitudinal coupling. So the coupling to the photon field and the splitting, in the same direction. This is possible because there's a very rich spin-orbit structure. We can choose then the electric field perpendicular to the structure such that we only get this component leading order. This is actually kind of very promising from theory, at least. We have shown now that you get a very good coupling, and there are a few labs now working on this. And it also depends very strongly on the geometry. So whether it's a rectangular wire or a circular cross-section or triangle and so forth. And one gets coupling on the order strength here on the order of a few hundred megahertz as a function of electric field. So for example, here this is a very nice switch. The electric field in this direction perpendicular to the structure turns on. Let's say for the blue one, it's for this silicon, for this structure here, reaches a maximum, then it goes down, and one can reach strengths, coupling strengths in the hundreds of megahertz. And in some of the structures, it can even go up to gigahertz. I'm telling this to a few ears, which might listen, that this is something which is extremely interesting, I think, from that point of view. Very promising numbers. And why is it interesting? So, for example, it has been demonstrated by Jason Better's group to couple, two qubits to the same cavity line. So it's possible we can have two distant qubits and couple them. So that means you have qubit 1, qubit 2, and then the coupling to the same photon mode. So the Z1 and the Z2. And if you have longitudinal coupling, this is germanium, this should be possible. This is not germanium here, but liquid germanium. Then it's rather straightforward to see that you get a coupling which effectively is an icing interaction between the spins. So if I integrate out the photons, I just complete the square here essentially. Then I get square. This couples Z component of qubit 1 to Z component of qubit 2. It's an icing interaction. And that's actually the best possible interaction for 2 qubit gate because it just is a phase shift. So if I go back, to the transverse coupling I showed you before, this one here, this is perturbative. It's rather small. I cannot make this large because I have to do this off resonance, and I have no limitation here. So this can be extremely large. And for typical realistic material parameters in silicon or in germanium quantum dots, one can reach then a switching time in a cavity of 2 qubits transmitted by a photon, standard photon on the scale of 10 nanoseconds. This is a very high fidelity. So this is a prediction which we make. Now the labs are working on this. So I think yeah, once this is demonstrated, this is a very important step for the further scale. Okay, so I rushed a little bit through the stuff here, so I'm at the end of my talk. I can read the summary if you want to read more for yourself. I mean, here's a list of reviews. Yeah, at the end of the talk. Thank you.
Any question? Silicon, germanium?
So you showed us some like really promising structures and said that these were promising for scaling up. What are the barriers to scaling up? Is it material imperfection, or is it just how hard it is to define the structures?
I would say, the main challenge people can see at the moment is to bring in and out the wires to control the structure, right? I mean, it's a great advantage to have small structures here, quantum dots, but you still need to bring the wires at least, let's say, 1 wire per qubit in the standard setup. But there are now ideas that you could use a so-called crossbar geometry, where wires go across a square, let's say. And then, the number of dots scales like n squared, n times n's, but the number of lines would then only scale linearly. And that could basically, avoid or beat this kind of scaling problem. However, and this is, another bottleneck then, you need very high kind of, dots need to be very, very similar. We can allow for many variations because basically you have only one line to control different dots, and so one pulse needs them to have the same effect essentially for each quantum dot. So you need to have very high fidelity in the construction of the dot. So if let's say the fabrication is at the level where you can achieve that, then I think that would be a very good way forward. Now, some people believe that is very challenging, so they go rather in linear structures, not just one line, let's say more like the IBM superconducting qubit structure, which is a little bit of a snake with intermediate connections. And that is also something which is kind of a two-dimensional structure. Scales kind of okay. That is also, I mean, that would allow then, for example, to have your but there are some ideas by, let's say, to have the CMOS technology control circuits on the chip and control then, let's say, such ladder arrays, and the next one, the next one, the next one. So this could also be scalable. And these cavities, there are ideas. So, for example, if you have a cavity and you have long distance photon coupling, this can go up to it's a millimeter. And imagine now you would have one-dimensional wire, could have millions of qubits in there on that length scale, and you can couple all-to-all. And all-to-all coupling is like two-dimensional, or actually it's infinite dimensional. So then you would also have a scalability in there. I mean, this is a little bit the game, for example, which is played in ion traps or in ion cube. So this is also linear and all-to-all. And so there are several ideas, and they depend on the technological advances.
Can I ask a follow-up? So if you can have a large line of nanofabricated devices, but some of them are slightly different, and so they are not what you're looking for. Yeah. Would it be possible just to talk to the ones that you want? The beauty of ion traps, of course, is the ions are all the same. Yeah. But in this system, could you just talk to the ones that are quote unquote good?
Actually, this is the idea, right? I mean, so first I should say, if it's an array of one-dimensional quantum dots, then they don't need to be added. So there it's not necessary. But still, would be good to know it's better, but it's not necessary. Now they can talk to each other, and I can make them talk to each other by a local gate. Just by a local gate, I can control now this spin-orbit interaction. Let's say turn on the coupling to the photon, and then number 5 talks to number 10. And if number 10 is not working, then I don't use it. And because it's not nearest neighbor, it's not hindering then the sign. So this would be an advantage when you have all to all, that if some of them don't work, then you don't care essentially. Yeah. That is similar, I think, in spirit, you know, like
Yes.
You probably said it, but I missed it. About this mysterious noise, you said that charge noise is of unknown origin. What is known about spectrum of this?
Yeah, that's a good question. Typically, it depends on the frequency. It's 1 over f noise.
Oh, it's one.
Yeah, but you know, it crosses over to other powers. Can also be 1 over f to some power alpha, which is larger than 1. And depending on that, one can make then some identification with other sources. Yeah. So 1 over f is indicative of you know, 2-level fluctuators.
Yes.
I believe you said that the noise was due to dangling bonds on the silicon surface. Is that right?
Yes, in some structures we know that. Yeah.
But I thought that don't they use hydrogen pacification for that?
Yeah. But you know, I think it's nothing is perfect, right? But I think this is another, you know, technological or even a basic physics question: how to make those dangling bonds completely pacified. Yeah, I mean, people are working on that. Yeah. For example, in the FinFETs, one of the problems is, you know, it works all nice on paper, on theory, but when you do the real structure, then there are also accumulation at points where you would not like that. And in some of the structures, they have to fight actually with spurious quantum dots, which are not at the apex, as you would expect, but sitting somewhere else. And this, you know, people try then to fight, let's say, with screening gates placed at the right point, such that fields are screened, and this does not happen. So there, it's a very rich kind of field.
Any other question?
What's the spin of a hole?
Okay, so I can answer here.
I guess they hear you.
Okay, so you know, the spin, the effective spin of a hole is 1/2. So it's composed of 3/2 and 1/2, but projected down in my subspace, it's just a 2-level system. And in a 2-level system, I just can label them now as a pseudo spin, as a +1/2 and a -1/2. So you know, sometimes people are confused, let's say, with a heavy hole. A heavy hole has a +3/2 up and -3/2 down. Then you think, oh, how can I go with one flip, you know, from up to down, right? I mean, it looks like as if I had to go through the intermediate. But in principle, if you factor everything in, that's an effective pseudo spin. This pseudo spin is 1/2. This is actually the story which I tried to tell with the splitting. So in the low energy sector, you get almost a 4-fold degeneracy. This 4-fold degeneracy is reflecting this spin 3/2, that you have 4 levels. But then by strain, you can lift them, and then just 2 levels are left, and they are very complex suppositions of the heavy and the light fold. That gives you an effective spin 1/2 in here.
Any other question? So you have to make a prediction, which one of these platforms will win. And then 20 years later, we can say, at the Colloquium in NYU.
Well, you mean now the ones in the spin qubit platforms?
Right.
They're already 20. And now, if you ask me now, you know, between the superconducting ions, atoms, photonic systems, and semiconductors, I would say, you know, in the end, if you still need 100 million qubits integrated, and you want to have it, let's say, you know, somewhere in a room like this, and not the whole building, I see no other possibility than semiconductor platform. But I would not really, actually, I don't think in the end there needs to be only one platform, because it could also be that one platform, let's say ions, are useful for some applications, and superconducting for other applications, and let's say semiconductors again for others. Because many of the algorithms which we now learn about, they have different demands. And you know, let's say if you can mostly operate X gates, and you can do this in one system better than in another system, then use that system, right? But from the point of integrability, look, I mean, a chip. I'd like to make this example: chip in your iPhone, right? The next generation will have about 200 billion transistors, not million. 200 billion transistors, right? And the size of a quantum dot is the size of a transistor. So, you know, for this industry, it's not completely crazy to think of such a high intensity of integration. This is optimism.
So if there's no question from Daniel, we can keep that optimism and go for wine and cheese. Thank you.